Yeah, good morning, everybody. Just apologize for the late start. Just give us one more minute for, there is a small technical problem that is delaying us. But again, just 1 or 2 minutes and then we'll be starting. Again, thank you very much for being here. And apologize for the delay. Okay, so again, good morning. This is the third day, third full day of the virtual ICD 2020, and we're starting. We had earlier talk from our sponsor, the Qatar Research Center, and now we're starting with the today's keynote. In today's keynote, we're very, very excited and very honored. We're very happy and honored to have Professor Vipin Kumar give the talk. Professor Kumar is a professor at University of Minnesota. He has an endowed chair, the William Norris Endowed Chair, and he has a huge impact in the area of data mining and also in parallel computing with a lot of research awards and a lot of impact in research. In fact, I should mention that he is a fellow of the Triple AS, American Association of Advanced Sciences. He is a fellow of ACM, he's a fellow of IEEE and of SciAm. And he also has been honored by the ACM CKDD 2012 Innovation Award. That's the highest award for technical excellence in knowledge discovery and data mining. And he also has received the IEEE Computer Science Sydney Fembach Award. So again, we're very, very honored to have Vipin give the talk today, and please go ahead and Vipin, please go ahead and start the talk. Just want to mention that if you have questions, you can use the Q&A function of the Zoom, and I will collect the questions and ask them by the end of the talk. And welcome everybody, and Professor.
Thank you. Thank you, Dimitri. And it's a pleasure to be here. And of course, these are very uncertain times worldwide. And just another reminder that there are certain problems that require cooperation among the entire humanity. There are problems that are of existential nature, and none of us can solve them independently. And we are seeing that process unfold in front of us over the last few months at a very rapid pace. And I'm going to talk about a problem that is different than that, but highly related in many ways. And this is about the earth and environmental sciences, the challenges that sort of are arising in that field. And again, the big commonality, of course, is that there are problems here as well that require global cooperation and cannot be solved by anyone independently. And yet the key difference is that the processes that are unfolding here are at a very different scale than the one that you're witnessing every day today. They are the COVID related processes unfold at daily and weekly and monthly scales. And the kind of thing we are talking about are unfolding at yearly, decadal, and century scale. And indeed, yesterday was the 50th anniversary of the Earth Day. So people have been aware of these challenges and have been trying to get together to be able to address them. And I think the key question the key point I like to bring across to you is not only make you aware of some of these challenges, but also show you the opportunities that our field has in addressing these problems, and in the process enriching our field itself. So that's sort of going to be my my agenda today. So what are the environmental grand challenges of the 21st century? And of course, some of the biggest challenge that you keep hearing about continuously, certainly for many, many decades now, and more so in the last few years, is about the climate change, impending climate change. And of course, before the COVID, there was a lot more focus on it. In recent times, literally every part of the world. Last year, for example, was the biggest, very costly European heat wave in Europe. 2020, just by looking at the record for the last 3 months, is predicted to be one of the hardest years in the history of recorded history. And of course, I can go on this list for a very long time. The reason there's a lot more focus now today as opposed to 10 years ago, 20 years ago, is that for a long time we thought that maybe these challenges are going to be, we're going to face the climate change, the worst effect of climate change, by 2100. And more we are realizing that it's going to hit sooner, much sooner than later, and it's going to have huge number of unintended consequences because of the biodiversity loss and all the other issues that come with it. So this is one major challenge, and of course it's in the news. But this is not the only environmental challenge. And what I want to sort of give you a sense of is there are a lot of challenges that are all interconnected, and to address one, you have to be aware of the other, and they all have sort of interaction with each other. So the second challenge, which is sort of unfolding irrespective of the climate change on its own, but made more complex because of the additional challenges because of climate change, is this problem of how are we going to feed the world where the population continues to increase. We were 6 billion people at the turn of the century. Now we are 7.5 billion people. And projections are that in another 50 years, we'll probably reach 11, 12 billion people, and we'll have to double the amount of food production. And many of the things that we did in the last 50 years, last 30, 40 years to improve the food productivity, those solutions are drying up, again, because of all of the interconnected issues that we are facing here. And for example, one of the things we have done, humanity has done, to cope with the increased need of food, going back to the earliest start of farming 10,000 years ago, is to cut more trees to make room for farming. And we have sort of gotten to the edge of it. And then you see this image here, where you see half of the image is right side of the image is dense forest, and the other half image is the oil palm plantation. This is repeating, this story is repeating in all of the tropical world and elsewhere. And the point is that now we're running out of this forest to cut, and we need the forest to save us from the threat of climate change. So there are, this is a problem by itself. Even without climate change, it could be a big problem. With climate change, it's a bigger problem because we need not only to save this forest for storing the carbon, but we also need need the agriculture to produce biofuel. Okay? Now, there is another story that's sort of unfolding on its own, which is on the scarcity of water. This is only a small fraction of the 3% of the water is fresh water on the surface of the earth, and it's coming under tremendous stress. And it's coming under stress irrespective, again, it's coming under stress due to climate change. As people know, that some of the biggest impact of climate change would be felt in the society through water, and the availability of water is becoming less and less certain. But the picture that I have here on the bottom right corner of the slide shows a disaster that happened primarily due to human actions. So it's a combination of things that are happening here. And what you see here on the left side is one of the largest freshwater bodies in the world, called Aral Sea, as it's shown in 1989. And you see the right side in 2014, just about 25 years, you can see that this entire water body dried up. And this change had nothing to do with climate change. It was primarily due to the way humans are using water. There were rivers feeding this lake, and this water from that river got diverted for agriculture, and it changed, of course, the lake and the ecology, and it's a major disaster around that area. So the water availability of water is a big challenge. That is that's going to be, we're going to be facing that problem. And then the fourth problem, which is in the bottom left corner, is talking about the water quality. That is, as we are, of course, making all of these problems worse, we have less space to grow food, we have changing climate, we have less water. And on top of that, another big challenge that's impending all over the world is the fact that our water systems are getting polluted. And this is a very complex story. It's unfolding in different places in many different ways. I'm just giving you one example of Lake Erie, upstate New York. And the green stuff that you see here in a glass is not a smoothie. It's not something to drink. It's actually water from the lake. And if you drink it, you die. If you eat the fish that drinks this water, that's poisonous. And of course, this is an extreme case that happens once in a while. But the water supplies all around the world are sort of getting contaminated. Cities are spending more and more money on water filtration or water cleaning, and it's all happening because of all of the issues that you're seeing in front of you. Okay, for example, as we try to feed more people in the world by getting more productivity from the same land, we put more fertilizers, and eventually this fertilizer sort of wash away into our water supply, lakes, and water bodies, and then it sort of creates situations like these, not just here, but all over the world. So these, all of these, of course, are connected to humanity's the issues that sort of connect directly to humanity. Energy, water, food, we all need to live in that, and they all interact with our changing climate. So these are massive problems that require global solutions, and are being pursued all over the world in all of the scientific communities. And the question is, what does our community of computer science, data scientists, data engineers, what contribution can we make to it? And of course, we have been making contributions to this area by providing better computers, better techniques for data analysis and such. But much of that work has been sort of a secondary nature. And what my goal in this talk is to convince you that there is an opportunity here for us to take a leadership role and And of course, the connection to that comes from the data, which is, of course, the topic of this conference. This is the golden age of data science. And I don't have to convince this audience that what our community has been doing for the last 2 or 3 or 4 decades has completely upended the way things are done in many, many aspects of life, going from transportation to commerce, to interactions, to entertainment. It's just amazing as to how far we have come. And the question is, for us, could we make the same transformation to addressing some of these environmental problems? Okay? And of course, connection, as I said, is through data. And of course, data in environmental sciences come in many, many shapes and forms and from many, many sources. Just to keep this talk focused, I am focusing only on one kind of data, which is the one that's being observed from the Earth observing satellites that are scanning the Earth every day to provide a very detailed picture of many, many processes that are unfolding on the Earth and environment in a way that wouldn't be possible, that wouldn't be imaginable just a few decades ago. And what you're seeing here in the animation on the top left corner is the animation of a satellite, a sensor called MODIS on a satellite from NASA, which is spinning, which is basically scanning the Earth and taking picture of every single spot every single day, just about roughly around 10:30 a.m. when I'm at local time. If you look up, the satellite is up there taking a photograph. These photographs are, of course, very coarse. A square kilometer has only about 16 pixels. So there's no privacy issue. These are issues that the pictures are very, very coarse. And yet these data sets, of course, this data set is made available to the entire world free of charge by NASA. And since then, this was the first satellite that sort of made public data available. Since then, many, many other sources of data, satellites are now becoming available. There's a very rich program from Europe, Copernicus program, that has a series of satellites called Sentinel series, and they're providing data very similarly. There's an old satellite that goes back about 40 years, Landsat, whose archive became public in 2010. And there are many, many commercial ventures that are providing very high resolution, high fidelity data at sub-meter resolution. So my point is that these data sets are there. Many of them are public. Many of them are scanning the Earth at different resolutions in space and time. And they offer tremendous opportunities to address some of the questions that I talked about in the previous slide. And in the rest of my talk, what I'm going to do is give you a high-level overview of 3 different areas where of some work that is done in our group on addressing these problems. Again, these are not comprehensive, but from the perspective that I talked about on the slide number 1, there are just 3 samples, and I will end with sort of a broader picture of what other things are going on in our group, and then of course in general elsewhere. And for each of these 3 case studies, I'm going to talk about what the problems are from the environmental perspective, and what innovations in computer science, in data science, in machine learning were required to be able to address them. And in nearly every one of these cases, the innovations that sort of that were required are being generalized to be applicable to many, many, many other applications outside of environmental sciences. So this is the interplay between advances in data science helping advances in data science required to address some of these environmental problems. And those advances then, of course, advance the field of data science as well. So, and again, for each of those 3 problems, given the limited amount of time I have, I will only have time to be able to tell you exactly what these problems are, very brief overview of what the challenges are that are being addressed in the new machine learning formulations, and show you some specific results to convince you that yes, the advances were made in environmental sciences. To get really more details on each of these technical aspects, you'll have to read the papers. So the first problem is being able to map the forest fires around the world, especially in the tropical zones. And the question is, why is this an interesting problem? The forests, of course, are amazing entities. They, by simply being there and by growing, they are among the most effective sinks of carbon. Okay? In the sense that just by natural growth every year, they absorb as much carbon from the atmosphere as is emitted by the entire transportation sector. It's of the same order, like all the planes, trains, ships, everything you can sort of imagine, automobiles, put them all together, the carbon emitted by them, and that's the amount of carbon that's absorbed by the forest if you leave them alone. The irony is that because of our needs of various kinds, including food and fiber, we end up cutting, burning and degrading enough forest to counter for all of that. That is, the amount of emission from this forest into the atmosphere is of the same order because of our actions as they are able to absorb carbon from the atmosphere by their natural growth. So one of the simplest, cheapest, and most effective way of getting to the zero carbon target is to be able to maintain our forest as it is. And if you want to be able to maintain them, you want to make sure they're not degraded and they're not being burned by people for different uses. You have to cannot manage anything that you cannot monitor. So being able to do this mapping is extremely important. And it turns out that the traditional ways of traditional automated machine learning ways of doing this monitoring actually fail because of the lack of ground truth. And I'm going to talk about the challenges in a few minutes. So it required development of an entirely new paradigm of being able to predict, to basically use, to build classification models when you don't have ground truth, but have a very, very poor quality surrogate in place of them. The second one, and of course, relates to the mapping of the growth of plantations in the tropical forest. So one of the things people do at a very, very large scale, and it's happening a lot in the tropical world, is a lot of these tropical forests are being converted into oil palm plantations, sugarcane, oil palm, paper plantations, anything related to it. And being able to, and then some of the largest corporations in the world have promised not to encourage such deforestation for these kind of plantations. So they have sort of promised not to source any products that are coming out of these recently deforested lands. But the big challenge they face is that how do you figure out which forests have been recently deforested? Because when you look at the plantations from the sky, they look very green. You see the one on the right side in the middle picture. And because they look so green, it's very hard to distinguish them from the traditional forest. So you have to sort of build a machinery that looks at the entire process of converting a forest from burning and then planting a forest and its growth to be able to understand exactly which location might have been recently deforested versus the one that have been around for a long time. So this required new development of new algorithm, and I'll talk about that very briefly. And as I mentioned in the opening slide, that one of the biggest uncertainty for humankind in the changing climate and of course and increasing population is the availability of water. And what I'm going to talk about is a novel machine learning based methodology that is providing first of its kind information that could lead to much better understanding of how much water we have and how it may be changing around the globe. So this is a very high level overview, and just I want to give you a big picture here, and then I'm going to go to each one of them one by one to provide you more detail. So the first one is about being able to map forest fires, and on the face of it, this problem seems very manageable using traditional machine learning framework, and indeed there are state-of-the-art solutions available from the worldwide ecological community. They mostly use standard machine learning algorithms to create these maps of forest fires every year, every month. And the idea is that you have data from the satellites, which can provide you the features. And if you have labels for where the locations might have burned or in the past, you use them to train your machine learning model. And then you apply them into the future. The biggest problem with this approach is that the models built in one part of the world don't work very well in the other part. So if you look at this globe, the picture of the globe on the bottom right part of the slide, you see that there are certain part of the world where we have very good information about the locations that have been burned. So for example, the state of California, which suffers from forest fire very frequently, at the end of each year, they would issue polygons, which will define the area that got burned in that year. Canadians also do a good job. But the rest of the world, the situation is much worse. Even in the rest of the US, it's not such a good quality. But the rest of the world is much worse. But the biggest part is that the forests that we need to save most critically are in the tropical belt. And that part has a huge scarcity of labels. It is not like you invest some money and get some more labels. The problem there is that most of the time, the tropical areas are covered by clouds. So if you look at the satellite pictures, most of the time, for most of the pixels, there is no data or hugely corrupted data. Okay? Then the second problem is that when these fires burn in the tropical areas, they create so much smoke that nothing is visible from the sky for a long time. You may have heard of the stories that when there's a fire in Indonesia, people in Singapore cannot breathe because the movement of smoke and cloud. So because of the combination of these issues, it's very difficult to construct ground truth for these locations. So as a result, to be able to monitor these areas, you have to somehow assume that you have no target label for supervision, but do use something surrogate. So for example, it's possible to be able to find out something surrogate, which is like there are sensors on the satellite, like the thermal anomalies, which look for changing the temperature on the surface of the Earth. And they, of course, can be, they're being measured every day, everywhere, except they have limitations as well. You know, if the fire is burning, they may not be, satellite may be not on top of the fire. Or satellite may be on the top of the fire, but could be occluded by smoke. So there are, so the question is, for the first one, what we're looking at is a situation where there are no target labels available, but we may have imperfect annotation of extremely poor quality labels that are useless by themselves, but they're available for every single sample. Okay, so that's the one problem. Second thing is that the situation we're looking at is a situation in which the target class of interest is highly imbalanced, which means many of the traditional supervised learning frameworks can actually break down, because even small amount of false positive rate can really mess up everything. And the third thing is, if you don't have perfect labels of any kind, then how do you measure the performance of an algorithm? Because you need to have some labels to be able to know whether you're doing well. Okay? So all of these problems sort of course, make it very, very challenging to develop a framework. And this piece of work, of course, required many, many different steps. I'm only going to focus on the first two. I'll provide you a little bit of technical detail for the first two, and but the third one I'm going to skip. But all of them were sort of required to be able to solve this problem. And in the next few minutes, just to sort of give you the some technical details for this problem, I want to sort of make you understand as to what do I mean by imperfect labels. So if you look at the two matrices here, the left and the right, the left one matrix here is a traditional setting for classification. You can assume blue to be positive, red to be negative, and you have features and you have labels. And if you had a perfect set of labels available to you, you can go ahead and build a classification algorithm. We don't have that in this case. What we have is the table on the right side, in which some of the positives have been flipped to the negative, and some of the negatives have been flipped to the positive. So alpha is the rate of corruption to the positive, beta is the rate of corruption to the negative. And of course, the right side is corrupted so badly that it's not very good to be usable as itself. And as I said, for the forest burn areas, I could potentially use imperfect labels. Thermal anomaly is an imperfect label. If I was trying to map the urban settlements on a global scale, I could use nighttime light as a possible surrogate. If I'm recommending items to a new user, I could be using interest of my friends to serve as a target label. And of course, the sort of list go on. Now, just to put this thing in a context of the broader supervised learning framework, most of the traditional work you find in the textbook is on the left edge of this tree, in which we assume we have good quality labels available. And if you happen to have sufficient amount of training labels, that correspond to the leftmost corner of this tree. And that's what you study in the textbooks. But if you don't have enough labels, then of course you do research. The huge active areas of research in semi-supervised learning, active learning, multi-view learning, But we are looking at neither of these situations. We don't have any expert annotated labels, so which means we are on the right side of this tree. Now, if you have imperfect labels, there are situations in which people have there are situations, for example, learning from the crowd. You know, you're looking at the learning from the Amazon Turks, where you have multiple people labeling images. None of them can be trusted, but they would be making mistakes, hopefully independently. So people have built a series of innovations in cases where you have many such annotators, each of them imperfect, and how do you sort of put them together to build a more coherent story about the annotation. But that's not the situation we are talking about. We have only one annotator on a global scale. Okay? Even in that situation, people have sort of talked about a situation in which only one of the labels, only the positives are corrupted, but the negatives are not. Okay? So alpha is non-zero, but beta is zero. It's called positive unlabeled learning or partial supervision. And there's a series of work that goes on in that area that actually is very good, but that's not the problem we are working with. We have both corruptions on both alpha and beta. Then in this branch of imperfect supervision, in which both positive and negatives have been corrupted, people have actually studied this problem going back at least 20, 25 years from theoretical perspective, and there have been more and more interesting solutions that have emerged in the last, actually in the last 5, 6 years, in the case in which the both positive and negatives are balanced. That means you have equal amount of positive and negatives, so you could use traditional methods such as accuracy to optimize them. And of course, we don't have that thing. We have like luxury, we have imbalanced class situation. And now the solution that had to be built actually happened to use all of these ideas from all of these previous directions to build a solution. And what I'm going to show you is the result of how that works. So this is the level of technical detail I could sort of talk about. So I'm going to show you results of what when this methodology was built. It's a 3-step methodology. It addresses all of these issues I talked to you about. That is, how do you work with imperfect labels and get almost perfect solutions? And the solution of this, the idea was to sort of see, can we build a map of what happened to the forest fires in this entire tropical belt on the globe? And this machinery is called RAPT, which basically stands for rare class prediction in absence of ground truth. And you can see this machinery found about 570,000 square kilometers of tropical forest burn in this belt. From mostly it happened in the Amazon and Indonesia. And it's actually 3 times larger than what is found by the state-of-the-art NASA product, and of course much more accurate. And there are papers that sort of talk about this product and how good it is. But I'm just going to give you a visual sense of this difference here. So if you look at just to give you sort of anecdotal evidence, you have 3 images in front of you, and the leftmost image is, and all of these images are from large area in the Amazon rainforest in South America. And you can see the leftmost image is from 2002, and it's dark green, and it has a few clouds, and it has some white, dark white, light white shades on the right side of the image, which are you can see if you look carefully, there are roads and some deforestation there. Now the same picture, if you see in 2015, there are no clouds here, but you see a lot more white shaded stuff, which is all deforestation. So if you look very closely, if you zoomed in this area, you can actually see those plantations and such on the ground. Now, on the very extreme corner on the third image, what you're seeing here is all of the locations found by this algorithm called RAPT, which did not have access to the ground truth because there's no ground truth there. And those locations that are found are mapped directly on the image, and you can see every one of those shaded image that you see in the middle is covered by the dots here. So it sort of tells you how accurate this paradigm is in catching these burnings of the forest, which of course preceded this deforestation. The second thing is you see 2 different colors, yellow and red. And of course, all of these points are found by this algorithm called RAPT, but the red ones were the NASA state-of-the-art algorithm found only a very small fraction, which are shown in red. So this sort of gives you a sense of how powerful new algorithms can sort of solve some of these difficult environmental problems. So there's the case study 1. So I'm going to now very quickly talk about the second case study, and I'll go through the last 2 very quickly. And this one is about the plantation dynamics in the tropical forest. And as I mentioned to you, some of the biggest corporations in the world have promised not to source any products from recently deforested land. And the question is, how do you identify them? And because this problem is so important from an environmental perspective, a number of products developed by NGOs have come up. For example, there's a product called PP. It's produced by an organization called Transparent World with the support of Global Forest Watch. And it's all based on primarily via manual annotations. And they produced 1 map for 2014. And it just turns out that this map is extremely inaccurate. It has it finds lots of plantations, but most of the areas, more than half of the locations that you see here, are not really plantation. And the other problem, of course, is that this is a map only for 1 year and not for every year, which is, of course, difficult because it's all manual work. There's another organization called Roundtable on Sustainable Palm Oil, they created 3 such maps, one for 2001, one for 2005, one for 2009. They're still in the process of creating one for 2014. It's again created mostly manually. It's much more precise, but very incomplete. More than half the locations that are really plantations are not in here. So this becomes sort of a big challenge as to how do you sort of take products like these, potentially use them as a source of training data and build machine learning models. And the challenges, of course, here are that these annotators are imperfect. They both have huge positive and negatives. And of course, we suffer from the traditional problems of heterogeneity in both space and time in these problems. So a new machine learning framework was developed. There's a series of papers on it, which sort of learn from multiple imperfect annotators handling temporal heterogeneity and incorporating process-based information. And as a result, what you have is this product, which is first of a kind product, in which you see all of these red locations, which are plantations as of 2001, and all of the green areas are the growth in year after year. So 2001, 2002, 3, 4, 5, 6, 7. So you can see the growth increasing. So you can actually find out from each location where the plantations are, when they were built, and how they're growing, and how the countries are responding to this international pressure for saving their forest. And you can quantify these things much more precisely. So this, of course, is a first of its kind dynamic product made available, made possible by advances in machine learning. But there are many, many other possible uses of this, especially when you combine this work with the previous case study we saw. So a lot of these plantations, of course, are legal plantation. That means government of Indonesia gave them a permit to create this plantation. But they have no, and they would expect people to cut the trees, move them out, and then put the plantation. But oftentimes the easiest thing for people to do is to simply burn the trees, clear the land, and then place the plantation, which is much cheaper because these areas are very hard to reach. So the question one can ask is, which of these plantations were preceded by burning and which ones were built in the proper way? And now, because of the first case study, we can answer that question. So here are all the locations that became plantations during the year of 2001 and 2014. Okay. Now, some of them were burned, and some of them, of course, some of them were preceded by burning, and some of them were built properly. So if you, on the next slide, I'm going to convert some of these greens into red. Those are the ones that got burned. So you can sort of see a good majority of these locations actually were burned before they were being placed as a plantation. Okay. Now imagine if you are in the dense tropical forest, and if you are trying to clear an area by burning. Once you start the fire knows no boundary. It could sort of spread anywhere, right? So if you look at this area here, for example, I don't know if you can see my arrow, you see this little area here, it's all red. That means this plantation was exclusively built by burning. It's in the middle of nowhere. Now, when you start the fire here, the fire has no boundaries. So the question is, what are the potential collateral damage? That is, when you're trying to build these plantations, how many other trees did you burn? And you can find that too using the case study one. And it turns out the blue is all of the collateral damage. So you can see massive damage that's happening in areas where people are trying to build plantations. So this gives you a sense of the kind of information that advanced machine learning algorithms can provide to address some of these big problems. The last case study I'm going to talk about rather quickly, again, is being able to map the water and its dynamics on the Earth, because we want to be able to understand how the climate change is impacting it. For example, there are glaciers in the Himalayas that feed rivers, which provide water to about 2 billion people on the Earth, and these glaciers are melting. And how fast are they melting? What is the impact of climate change on them? We talked about the Aral Sea, which is the water changing in response to human actions. And of course, we all suffer from the extremes of related to water, like floods and droughts, and then how do you sort of get a better warning system for those. So all of these require a better understanding of stocks and flow of water from many, many different perspectives. And so the question is, so let's see. I think one of my slides is missing here. So basically, the biggest problem that we face here in this case is that the water, even though we have plenty of labeled data for water, to the extent that in year 2000, NASA flew a mission of the space shuttle just to track water on the Earth. So 1 month, the shuttle did nothing but shoot radar screen on the Earth so that we could figure out which locations are water. But that's a single snapshot of the Earth for one time. The water bodies have been sort of growing and shrinking over a period of time. And the question is, can we build, using that data, can we build a model, machine learning model that works globally? And then the problem with that is that there's a lot of heterogeneity in the way the water and land sort of looks around the globe. That's the left part of the picture, which is sort of hiding here. And the right side, I'm sort of trying to show you another aspect that's sort of faced by many of these machine learning algorithms that work on the remote sensing data from the satellites, is that most of the data, most of the time, is missing or extremely poor quality. So in the picture an image you're seeing here, anytime you see a dark orange color, data is missing. So which means most of the time, a lot of data could be missing. And when the data is not missing, it could be so poor quality that you have is the features that are poor quality, not the labels, that you may actually, your classification actually may be giving you bad results. So then you have to figure out entirely new machinery of machine learning algorithms that can possibly use the underlying information about the physical laws and other processes that are unfolding in the learning framework to account for some of these errors. And again, that's a very powerful paradigm that has sort of gone on to have contributions in many other disciplines as well. So what I'm going to show you in the next 5 minutes is this a system created to monitor all of these water bodies on the surface of the Earth. And there are a series of such systems because some of them use the coarse level MODIS data, which is available every day, which is half a kilometer pixel size, which means a square kilometer is broken into 4 pixels. And then there are other products we have available. I'll talk briefly, which look at the daily time series at the 30 meter resolution, and then others that use the Sentinel European data, which look at the data at the 10 meter resolution. And so, of course, the algorithms, of course, are independent, so they can be used at finer and finer resolutions of the Earth size data. So I'm going to show you. I'll give you a sample of what this viewer looks like. You'll see local and regional change analysis. You will see detecting melting of glacier lakes, changing rivers, identifying construction of reservoirs, and so on. So if you went to the system, it will sort of show you, the little dots, which are sort of representing water bodies. One of them might be, for example, this dam in Mexico, in the country of Mexico, Don Martin Dam. The system would let you sort of see how big this water body is on different days, going back to 2000, and how many pixels does it have. Each pixel is 1/4 of a square kilometer. And you can see at the peak of its water body, it's about 200 square kilometer, 800 pixels. And it's, of course, been going up and down. And if you want to really verify this, you can look at this Google time-lapse image, which provides you annual images visually for any part of the world. And you can see that this annual time-lapse from Landsat data is confirming growing and shrinking of this water body pretty much the same way. You can color these water bodies in the sense of whether they're increasing, I'm coloring them red here, or decreasing, which is blue or green. And you can see, a lot of green and reds all over the South American continent. Let's focus on one of these green area, which is multiple thousands of square kilometers. It's a very, very large area. It's larger than perhaps it's like at least about 1,000 kilometer by 1,000 kilometer. And you can see a lot of water bodies here, and they're all related to agriculture. And then if you see the total sum of these water bodies was as high as 10,000 pixels, which is about 200 square kilometer. And it again shrunk very recently. And you can see that process unfolding by clicking on any of these images on the viewer, and you will see that, yes, these water bodies are shrinking dramatically in recent years. You can also see these water bodies increasing. So you see all of the red spots in Tibet, which is what people suspected. But except that before this kind of work, people would build Landsat level maps only for small regions for a specific year, except that now we can look at any of these areas through the system and figure out exactly what's happening. So you can see in any of these inlets, the black areas are the lakes that are existing, and the red areas are the ones that are increased. And if you do, again, time lapse, you can see all of these areas increasing. And then the best part is that you can accumulate, given this information, you can figure out exactly what is the totality of shrinking or growing that's happening here. You can figure out over the last, in a period of 15 years, the amount of surface water in this area actually grew by about 10,000 square kilometers, about 40,000 pixels, which is a massive amount of area that's growing. And of course, this means the lakes are getting bigger, but there's more water in the river today. But pretty soon, these glaciers will dry out, and there'll be billions of people in the world who will have no water for agriculture. You can see the rivers meandering all over the globe, because whenever the rivers meander, some parts would lose water, some parts would gain water. You can see any place where you see green and red point next to each other, you can see river meandering. So river meandering is something ecologists study for very important reasons, but they have to study one river at a time, and this provides a global view of this entire process. You can see islands shrinking in response to the rising oceans. You can sort of see the blue area sort of shows the parts of the island that got shrunk in this viewer, and you can see that in the time lapse, the island shrinking on the bottom right corner. You can see islands being, the reservoirs being constructed. Now, reservoir construction, because the river body would be small before, and then it will sort of grow up to be something larger. Now, reservoirs are so important that people actually in ecology and hydrology and many of these sciences, people actually have built a database called GRAN, Global Reservoir and Dam Database, which actually was built at the end of 1990s with very careful manual construction. So it was reasonably complete until 1990. And then after that, it has been relying upon people to report additions to it. And there are only about small number of additions in this database since 2001. But using this machinery, we can find hundreds of them all over the world, almost 2 orders of magnitude more dams all over the world. Now, this was, of course, a very coarse resolution product. We are in the process of releasing another product which is unique of its kind, which gives you information about 750,000 water bodies around the globe that are that's a more comprehensive than any other database that's available in the world, and it picks up any water body that's more than 0.1 square kilometers, so more than 10 hectares, and it covers the area where more than 95% of the population of the Earth is located. So this is where the action is in terms of water, and it provides the ecologists all sorts of information. And just sort of a last result I'm going to very briefly talk about, and this is using the Sentinel data from the European program Copernicus. It's possible to use the series of algorithms I talked about, in addition to some of a new framework in deep learning, to be able to monitor the width of these rivers as they're flowing over a period of time, which is a unique capability that allows calibration of these hydrological models that we rely upon every day for providing flood and drought warnings. And this is a game changer, because for most of the world, in most of the places, we don't have this kind of information available. And this framework allows us to see this information anywhere on the globe automatically. So with that, I'm going to sort of end to the closing, a few slides. So what I talked about is the use of machine learning in the context of data from these Earth observing satellite to address some of the key questions in environmental sciences. And this is part of a number of projects, including one that sort of a recently completed project called Expedition in Computing Project on understanding climate change. And this project, of course, like many others that we're involved in, involve computer scientists, but also ecologists, civil engineers, environmental scientists, climate scientists. And we work not just with the remote sensing data, but also the climate modeling data. And the questions that we sort of study are not just land cover changes, but climate teleconnections, what may be happening to the oceans, what may be happening to the extremes. And I mentioned to you the early work about the water quality on the opening slide. And some of the ideas that's emerged from what you heard today have led to a new paradigm of building hybrid physics data models, because a lot of these water quality questions and ecology questions are handled using physical models, but then physical models are always inaccurate. So how do you bring machine learning to work side by side in a synergistic fashion with these physical models? It has sort of created an entirely new paradigm, and it's leading to new solutions that are being deployed by USGS in operational setting. So this next slide is just sort of showing you that a work like this, of course, leads to publications in the traditional computer science journals and conferences, but it also has impact outside computer science and many other venues. So it's inherently interdisciplinary and with a huge impact. So now with my last, so you see, publications, of course, are more than half the publications are outside of computer science, and most of the students who work on these topics actually work very, very closely with domain scientists as well. So with that, I'm going to conclude on my last slide, which is just to, I'm hoping I have convinced you that all of these big data that's becoming available in environmental sciences and climate domain offer great opportunity to increase our understanding of the Earth, climate and environment, and the problems we are facing. And addressing these challenges that are unique to these problems require methodological advances in machine learning. So you need to develop completely new approaches. And once these approaches are developed, they actually have applicability not just in these problems, but also they can come back and improve and advance the state of the art in our field as well. Okay? So with that, I like to thank everyone for their patience and listening. And here is some of my team members and, of course, collaborators across the globe and across different institutions. And I'll be happy to take any questions.
Well, thank you very much, Vipin, for the very, very interesting talk. And I see there are actually a number of questions. You can also see them in the Q&A box, but I can...
I'm not able to see them right now. Oh, okay. Maybe I can see them now.
Okay, so
I can see them now. I can see them now. Yeah, but it'll be good if you can read them, so I can answer the ones you read. Yeah, that's a good idea.
Okay, so Lily Xu is asking, could you talk a little bit more about how to evaluate the performance of a model that has imperfect labels? For example, in your case of the forest fires.
Yes, yeah, very important question. So as I said, if I have no perfect labels, then how do I know that my algorithm is working? And this is the problem we faced. We built a paradigm, and just to give you a background, and I didn't go through the details of the paradigm, it assumed imperfect labels, but it used the traditional methodology that we have in machine learning. We assume the imperfections are class conditionally independent. There's a tradition that goes back to 1995, originating with the work of Tom Mitchell, who showed that if the labels are randomly perturbed, and if you have enough number of samples, there's a possibility that you could build a model which is going to be just as good as if you were given perfect labels, provided you have enough number of imperfect labels. And of course, it was not a constructive proof. It was a theoretical proof. And then since then, huge number of researchers in different subcomponents have developed new machinery, and of course, we build on that. Now, the question is, if I build the machinery and if I show, we sort of showed proofs that yes, if the labels are class conditionally independent, it really works. But in a real setting, the labels will not be class conditionally perfect. The labels are what they are. So some places the paradigm is going to work and some places it's not going to work. So when we built the system and deployed it for the entire tropical area, what was happening was that in many places we were finding extremely good quality results. And in some places we thought we were finding something, but we could not verify them by visual inspections of the areas because the area was so cloudy. So that's where we had to actually handle this aspect. Without that, we weren't able to release it as a global product. And here, what happened was, even though we were not able to give a perfect sense of what the overall performance would be, but we were able to build lower bounds on the precision and recall. combinations, and that allowed us to make statements that yes, oh, this is a part we cannot. This is an area of the world where we cannot trust the results because the lower bounds are not good enough. This is the part where we can trust the results because the lower bounds are high enough that we can trust them. And it's a very interesting piece of work. You'll have to read the paper. If you send me an email, I'll send you the direction to it. But it's a paper that appeared in IEEE PKD a couple of years ago, and one section of that actually deals exactly with this problem. Okay.
Okay. So you're saying you can actually build lower bounds on by looking at the data.
You can build lower bounds by sort of, you can get some sense of what's happening, even though it's not a perfect sense, because the labels are imperfect, but from that you can still get a sense of how loose the performance may be. In some cases you say, look, I can give you very little guarantee, so maybe things are not so good.
Okay. Thanks. So the next question is by Jiangwu Wang, and he's saying, thank you for the excellent presentation. And the question is, what challenges you have to meet to have your data science work and your findings? So you want to have your findings accepted by the research community. What are the challenges in getting the research community to accept this kind of work? That basically, I assume this means that people are used to work with models, but now we're talking about the data as the model, right? And this is different to how people think in some of this.
Another excellent question. And again, this question, of course, is faced by anyone working in computer science who is working in the interface. That is, we are used to building methods and algorithms and software, and publish papers in conferences which sort of would work on benchmark problems. Now, when you go to the scientific communities, they are about solving problems, advancing science. And they, even though many of these subcommunities have started using machine learning, for example, the environmental science community uses traditional techniques like decision trees, random forest, and more recently even deep learning to solve some of these problems. But for the most part, these guys are interested in advancing the scientific frontiers. So which is why it becomes a very challenging to sort of work together. So 20 years ago, when I started in this direction, it was much harder. You really needed a really top quality collaborators who were interested in working with you to be able to make these advances. Today, the situation has changed quite a bit. There's a conference called American Geophysical Union, which is attended by about 30,000 eco-scientists, hydrologists, environmental scientists, aquatic scientists, any kind of environmental question that people are addressing globally. 30,000 people come, and I have been sort of going to this meeting for 20 years. Until about a few years ago, the most people would sort of take this area of data science with skepticism. In the last meeting in San Francisco in December, more than 10% of the sessions at this large meeting connected to machine learning. Same thing with American Meteorological Association, same thing with American, so basically there's a lot more interest there, but still these people are very wary of gadgets that people throw at them. They want to understand science, they want to advance science, not just work on benchmark problem. So it requires a very close collaboration, and you have to show that the products that you're building are beyond what they can ever do. So for example, I showed you the surface water product. USGS in the United States is responsible for measuring all of the water bodies on the earth. So, and then they have to have a map for the US for all the water bodies. When we put our map on top of their map and they saw in the US, they were missing huge fractions of this water body. They were very surprised. They sort of say, hey, look, this is very, very interesting. Similarly, when a machine learning plus physical modeling paradigm improved the forecast for the modeling of the lake systems, it's like it's something they can see without, they can see that this is advancing beyond the state of the art. So I think this is what we need to do. We need to solve the real problems. We need to solve the problem that they could not solve before on their own. And when you do that, then you get respect. And many of these papers that I showed you are published in the top journals, the #1 journals in their discipline. So, and of course, you have to advance the state of the art to be able to do that.
Well, thanks a bit. Let's go through some more questions. We started a little late, so but we'll try to kind of not take too much time from the next the award ceremony. Lax, I gave a question. So you gave three individual problems. All of them are about climate change, interconnected. Do you see any way to actually address these problems more holistically, not like three different?
Again, a very good question. So I want to remind people that the problem that I talked about on the first slide are dealt with in literally hundreds of subdisciplines, okay, individually. Okay, so for example, there are people who would study the lakes. There are people who study the rivers, the hydrologists. The aquatic scientists don't talk to the hydrologists. There are remote sensing people who are sort of studying the images from the sky. So there are many subcommittees that are studying it. So, and a lot of these problems are interconnected. And what us coming into the picture, data scientists coming into the picture, allows is many of these problems to be collectively studied together. And I'll give you an example of how, some example of that. So in the very last two cases I talked about, being able to map surface water and being able to understand the quality of the water quality system. So the hydrologists, there are aquatic scientists, again, two different communities. There are people who are looking at global hydrology, which are looking at the amount of water available. Now, there are three completely distinct communities, and yet data science can impact all three of them, can build methods that impact all three of them, and then have all of these people come and work with each other. So it's basically the real problems are multidisciplinary, and I think we can make these bridges work much more easily than perhaps they can do it themselves.
Data science is like a global language, right?
It is the global level. That's exactly.
So Chris Clifton had the question, but then he said his question has been answered. I mean, basically, he was asking about how do you validate the data, because most of the data is remote sensing data.
Yes, yeah. So I think, Chris, your question is how do you validate this? I talked about this. How do you find there are significant regional latitude etc. differences that the model must account for? And again, that's the biggest challenge, because the heterogeneity in both space and time. So it's not just latitude because of the temperature. It's regional because even at the same latitude, longitude, you could have ecologically sensitive zone. You can have droughts. You can have deserts. And each of them come with a different property. So, which is why some of these global products for finding the surface water have failed miserably, because they would, whatever traditional technique they would use would work in some places where they would validate, but they would apply it everywhere and they will be missing information. So, so the ground truth, of course, is so a lot of the so for the case of forest fires, the ground truth was validated by a very painful sort of validations that happened to be done over a period of 6 months. And again, it was very limited validation, despite the fact that you spent quite a bit of time. But it was the most extensive validation done for the tropical world that anybody attempted for the case study 1. For the case study 2, we used the high resolution data from digital globe, which had samples of very high fidelity data in different parts, and wherever we had available, we validated it. For the water supply, for the water and reservoirs, again, Google Earth sort of came into picture. So there are many different creative ways you have to use to validate this. So validation in all of these is not very easy, but you have to sort of work from many different angles. Validation for modeling the lake temperature and quality. We're working with USGS because they have extensive data for certain part of the world, certain part of the US, and that sort of enables these things. So you have to, this is the real world, so you have to do many different things.
Thanks. Yeah, a couple of related questions by Naum Chan and Lei Chen. The first one is, what kind of network analysis do we need for these applications, and what kind of models machine learning approaches are more practical in handling these cases? Because you have data, Yeah, go ahead, please.
Okay, so I'm reading this question. Which types of network analysis do we need for these applications? Now, this is a very broad question. So for the first 3 case studies that I talked about, network analysis took a back seat. But when I showed you the bigger picture in which a comprehensive set of projects, one of them talked about network really connections, which is trying to figure out which component of the climate connects with what other components. Now, that's a very rich direction that started with some of our own work back 20 years ago. And it's actually grown quite a bit. There's being able to take the climate system, represent it in the form of a graph, with each node of the graph is a region, and each link is talking about a relationship, which could be positive, negative. And then from these networks, how do you understand the spatial temporal patterns in them? Now, there are a series of papers our group has written, and of course in computer science venues. But the best part that I like about that is that there are 3 papers which appeared in top climate science journals, which talked about the entirely new phenomena discovered by climate scientists that would not have been possible without understanding of these network-based analysis of climate networks. So you would see, once you, of course, build these networks, then we have to build entirely new techniques to analyze these networks, because there's a huge amount of spatial and temporal autocorrelation in these networks, which is not present, which are not the issues that are present elsewhere. So I think we'll have to sort of go to those papers to be able to read more of these details, and I'll be happy to share them with you.
Okay, so this is looks like it's a very interesting topic, and I would like to suggest to everybody to continue this discussion in the Slack channel. The Slack channel is open, and it's going to be there. So Vipin, if you please hang around and maybe ask, not ask, answer some of the questions in the Slack channel, that would be great, because we didn't allow for any time between this and the awards. And I know we're about 15 minutes, so probably time to wrap up. If you want to answer one more question, or would you prefer to have people ask in the Slack channel, and then you can answer there?
Okay, you want me to answer one question?
I would suggest, ask the people that have more questions. They can ask them or unanswered questions, because there are a couple that we didn't go through. Ask them in the Slack channel, and you can hang around for a while and answer these questions there. Is that okay?
Very good. Yeah, I will do that. I'm reading some of these questions, very interesting, and I will try to type the answers to them, and I'll hang around for another 15 minutes.
Okay,